Hey, and hello, namaste. Welcome everybody to the Transitional AI Seminar Series. This week we have Mr. Ratnil Dev from the University of Sydney. And Ratnil is a second year PhD student now. And his research area is in the area of machine learning, computer vision, and applications to reef monitoring and visualization, more specifically in drill core analysis. Ratnil has a master's degree from the University of the South Pacific, and he has done some research in the area of cyclone prediction. And I was lucky enough to have him as my student and be his supervisor, and also lucky enough that we are both working together now in this project. And so with help of Professor Jody Webster and Dr. Kristen Sales, who are not here. Okay, give the floor to Ratnil to begin his presentation.
Thank you, Dr. Chandra, for those lovely words. I did not expect that end of the introduction, but hello to everyone on Zoom land. Today I'll be presenting the results of my initial or first work that I've done as part of this PhD program, where we are trying to use a clustering framework for data fusion and segmentation of the pools. So, first question that we have to answer is, why do we want to even study corals, right? So that's the first and foremost question. And to answer this, there are various reasons why. The first one is it gives direct sustenance to more than 500 million people in the world just from fishing. That's just the direct impact that comes from the Ocean Climate Organization survey. Also, in terms of its contribution to the climate, it stores about 70 to 90 megatons of carbon per year in terms of carbon capture from the environment. And that's more of on a global level. If we look at in the context of Australia, just the Great Barrier Reef says that the total value of the net benefit from the Great Barrier Reef to Australia is about 56 billion AUD. And its economic contribution directly from tourism and all those is about 6.4 billion, with 64,000 jobs being created by just the Great Barrier Reef itself. So these are just some of the reasons why the study of this coral is important, right? So when I say corals, or when I initially got into studying corals, I assumed I would be treated to something like this: beautiful anemones, beautiful corals, loads of color, and just looks pristine, right? Maybe if not that, then even a dead piece of coral that's found laying on a beach, that would be also nice to work with. But unfortunately, in this study, we are focusing on fossil reefs. Now, why are we using fossil reefs? It's very important in terms of storing or providing valuable data for reconstructing the paleo environment. On the figure on the right by Moose et al., they use the coral reef and they use the fossil reef rather to determine how the sea level has changed through time. So the sea level has a 100-year periodic cycle, goes from minimum to, let's say, goes minimum to maximum. The meters, I don't remember at the moment off the top of my head, but there's a 100-year cycle, and those cycles, sorry, there's a 100,000-year cycle, and those cycles are really well captured by coral reefs. So that's one of the reasons why we are focusing on studying fossil reefs rather than just the modern reefs itself, because of the history it captures. So where are we using the data from? Where's the data coming from? Comes from the Great Barrier Reef in Australia. It's it's to the east of to the east of Queensland and Cairns. This data was gathered with the help of the IODP expedition 325. In that expedition, they drilled Great Barrier Reef across various sections, and they had 34 boreholes across 17 sites all through this region. And these sites were varied in terms of which part of the reef was drilled, whether it was drilled on the outer reef or the inner reef. So various different locations were drilled. And let me just go over a few terminologies that will become more relevant later on. Is when a borehole is drilled, right? That gives rise to a core, right? But a core or a hole, rather, it gives rise to a hole that has various cores coming out from it. For example, we are drilling core 1, right? And from that core 1, you cannot drill, let's say, 100-meter section in one go. You will do that in sections. So each section is then stored as a separate entity, a separate core. So core 1 will have various components. Core 2 will have various components. These are denoted by the various numbers associated with it, which will make more sense when I go to the next slide. So if you look at the image 1 here, that's what I'm talking about. All of these images, or all of these drill cores rather, come from one specific drill hole, right? And they are then separated in terms of when they were or where in that particular hole do they come from, at which particular depth interval, and sometimes when drilling the core, it breaks in half. So that's why you have these kinds of various images accumulated. So what happens is, once those drill cores are recovered, there is a 2-level inspection done. There is the first level inspection done where the scientist that is getting those cores takes various physical properties, measurements on it. These physical properties are the field wave velocity, the gamma ray density, magnetic susceptibility, and the resistivity of the core. And these are taken at 10 centimeter intervals on a particular core, right? So that's one type of data that we have, that is the physical properties data. The other type of data that we have are the core itself, or the core image data. So we have these two types of data, and that is what we are going to work with. So what is the problem that I'm trying to solve in this study or in this paper is, given a particular core section of that particular core, we have to figure out what is the composition of the elements in that particular core section. So it can be made up of passive corals, microhalides, coralline algae, sand, silt, or encrusted corals, and that has to be done, right? And a manual map is created. Now, this is okay for doing with one image, one core, but if we go to the previous slide, there are 34 holes, 17 sites, so 34 by 17, and each hole has approximately an average of 40 meters of force. No, sorry, not 40, 13 meters of force, 14 meters of force. So these measurements that I am showing you are taken at 10 centimeter intervals. So 13 by 17 by 10 centimeter intervals, and a human has to then go ahead and analyze all of that to create this pretty much annotation of the way of all the four segments. So as it may be evident here, that's a lot of manual work needed, right? So that's one problem, right? There's a lot of manual work needed. Now, the other problem in this particular data is there is a high imbalance in the availability of the various classes of data. So there's a lot of sand. As we look at this graph on the right here, there's a lot of sand in our data set. And there's high imbalance between the low abundance encrusted corals and the high abundance of sand. So that's two problems. The first problem we are tackling is trying to annotate it, right? But while we are trying to do it, and if we are trying to use machine learning in this case, the problem that we are facing is there is high imbalance in the data. So we are trying to solve a imbalance problem while also trying to do annotation. So it's a two-step process. So what has been done? There has been loads of work in literature done on trying to use some kind of machine learning for classification of corals, but most of these work has focused on living corals. There exists very little work in literature that focus on identifying corals from the fossil reefs. So that's one of the things that was a challenge to overcome because there exists no data in literature to do this. We are supposed to do this ourselves. So what I'm basing this project off is paper from Tanya Insua, and what she did was she went and she's the person that took all of the cores that came from that expedition and labeled what are the species or what are the various classes of corals or elements present for each of those four segments. And what she then did was she just looked at the physical properties data, created a label for that physical properties data, and then trained supervised learning algorithms to just predict the class of coral that is present in that fossil using the physical properties data only. That had nothing to do with the image annotation, right? So what I'm trying to do now is develop a framework that uses some kind of clustering, right? Or various kinds of clustering rather, to fuse the physical properties data that has been already annotated with the image data that exists from the cores that have been built and create a annotation or create a scheme that is able to annotate and predict both at the same time. So that's the workflow that we came up with. We had the image data and we had the physical properties data. We take the image data, we try to remove the background from it, and in order to annotate, we first need to figure out where does a coral start and where does it end. So we first cluster it to find the various corals within it. And we already have the labels from the physical properties data. So the idea is to train a machine learning or classification model to then predict the label of that particular cluster, right? So that was the overarching goal. Now, just to confirm, this is a semi-automatic annotation scheme because in order to fuse the two models, it was not feasible for us to do it automatically. We still need human intervention in terms of taking the results from clustering and taking the result from the classification module and combine the two to create the annotation. So I will go over that more in the results section. So the methods for clustering that we used three different methods. The first and foremost that's used by each and every person that has ever tried clustering is k-means clustering. Why did we use it? It's very easy to implement, very easy to understand, and it gives fair performance for what it is. Now, it does not scale well to very large data sets, but it works. So we used k-means. The next one, we used hierarchical agglomerative clustering. Now, why did we choose HAC? Because we do not know how many clusters are present in a image, how many different classes are present in each of the cores. And since we can have different number of cores or different sizes of cores, the classes per core would vary. So in that case, we chose that, okay, HAC it does not require any number of clusters to begin with. So was a good fit or should be a good fit to work on this particular problem of clustering the various coral elements. Now, this model, however, is very resource intensive, and if we feed it the entire image of a core that I show here, okay, if we feed it this image in full high resolution, that model doesn't work. It fails. It requires too much computational power in order to find the various clusters, because it's a very basic approach where it goes pixel-wise comparison between each of the X thousand or X million pixels in that particular image, and to build its basically hierarchical model which uses to then separate the various components. So because we were using this model, which the intuition I've explained, we had to take our initial image and downsize it. So we scaled it down by 90% because the image was around 6K resolution, which we did not need. So we scaled it down by 90%. And the result I am showing you here, this image, this is the scaled down version. It is the lowest version of this particular image. So we scaled it down and then fed it to our models rather than using the full resolution. And the third model that we used was the Gaussian Mixture Model. Now, the rationale behind using GMM for clustering was both the k-means and the hierarchical agglomerative clustering, they are hard clustering methods. Gaussian Mixture Model provides some kind of soft clustering, and basically, since it uses a mixture of Gaussians, it is able, or it should be able to identify regions where one type of coral is embedded in another type of coral, or vice versa, because it's in these fossils that we have very complex situations where drawing a hard line between the two classes is difficult. So that's why we chose GMM, because of its properties of being able to do soft, having soft transition boundaries between the classes. So we took the various models and we ran it with anywhere between 3 classes to 10 classes for one of the test core, right? The core that we are using, this comes from core 33A of that particular large data set that I explained before. And with each of the clustering methods, basically we chose different number of K, basically different number of components, and try to figure out which model is working best. Now, in this example, we are using the silhouette score and the Kalinsky score to figure out which is the better model. And the Gaussian mixture model was giving the best silhouette score. Right. Now, that didn't make a lot of sense to us. So what we did was we went further and did a visual analysis of one of the sections or two sections within the core. So if we look at this example, if we look at this large coral piece, right? It looks like all of the models are doing almost the same thing. But if we look closely, the k-means is taking one large coral piece and saying that there are many other types of, or there is another class of element within that particular coral. And it's saying that there's a lot of abundance of that. So the light blue is like the massive coral it's supposed to be. And this dark blues, it's trying to figure out that maybe there's something else there. Same thing with the hierarchical clustering. The dark blue is the massive coral and the yellows are the other element it's trying to find there. But if we look at the GMM model, it is still doing that, but it's doing it less. Right? It's not more pronounced. It's not finding so many elements as the k-means or the HAC model. So that's how we figured out that, okay, since GMM had the best silhouette score, and after visual inspection, we saw that GMM also had less within class segmentation, we concluded that is the best one. So we reserved that. Then we moved on to the classification model. So here we went to the physical properties data that we already had, the labeled training set. We used that labeled training set, split it up into 70-30 train test split, and just fed it to 4 classification models. Support vector classifier, we used multi-layer perceptron classifier, and we use the random forest classifier. The last one, k nearest neighbor classifier. Why did we choose these 4 classifiers? Firstly, the paper that we based this we took this data set from, they used random forest classifier and support vector classifier within their project, and they proposed that there is scope to use neural network model or any other model to work on this particular data set. Another thing that was done in the initial paper that we are improving on is, in the initial paper, the data set was imbalanced. So they just did upsampling and downsampling to balance that particular data set. And then they came up with their testing performance. In our case, I am using, I forgot the name, but I am balancing the data with smoke. I'm balancing the data with smoke and then using the classifier on the balanced data. Now, I don't show the comparison between the unbalanced and the balanced data here, but the balanced data performed best. Therefore, I'm only reporting the result for the smoked balanced data or in this particular result. So we took the physical properties data, we balanced it out, and we trained the various classifiers on it. Now, this is a multi-class prediction problem. So in order to find the best model, we looked at the precision recall and the affluence score, as well as the overall accuracy, recorded all of that, and use the macro average AUC score to pick the best model. In this case, the best performing model was the random forest classifier. And if we just compare the SVC and random forest classifier, we can see that the random forest is doing a much better job at classifying the classes accurately when we look at the diagonals. The minority classes, although we balanced the data, was not really well captured with our other classification algorithms. Random forest and neural network model, multi-layer perceptron model were the best performing models as seen in this particular results. The KNN was also doing good, but the SVC was not really good in terms of the prediction. So we took the random forest classifier, right, and fed it. After we know that that was the best performing classifier, we fed it just the core that we had segmented. So we had segmented core 33A, and we fed it to our random forest classifier. Now, just for comparison, we also did that for the other classifiers as well. It was simple to implement. And we got these predictions. These predictions are basically, this is the core from top to bottom, and these colors represent the various classes that have been found within that particular core. Right. So the random forest says that at 10 centimeter, there is some coralline algae. At 20 centimeter, there is a massive coral there. Right. So that's how we interpret these results. So the last step, the annotation step, we took the prediction from clustering, and we took the prediction from our random forest classifier, and we did a side-by-side manual annotation. So we mapped, okay, this large blue region is supposed to be a massive coral. So we created a bounding box around that region. This region is a massive coral. The orange microbialite region, this dark or brownish light brown area is supposed to be microbialite. And for some reason, there was prediction of sand in this particular case. So there was no sand in this particular core. So we labeled those as misclassified. So that's the result of what we have done in this particular, in this paper. So what we did, we took the cores and we annotated them. Now, this was a very challenging task because one, there was no data present in terms of labeled data to directly annotate. In order to annotate, we had to use the physical properties data and link it to the image data and then annotate both of them together. So we used supervised learning for our labeling, and we used unsupervised learning for creating the sections within that particular core. And finally, we were able to manually create those annotations. We found that GMM was the most effective. And another thing that we found was, which I didn't highlight much on, when we were clustering our data, let me just go back. I skipped this, so let me just go back. When we were clustering our data, what we thought was, okay, why not just, instead of clustering image data, we also have physical properties data of that particular image. So we stacked both of them side by side, right? Appended the physical properties data to the image data, right? And then did our clustering. So we compared both of the clustering on just the image data versus clustering on image data plus physical properties data appended to it. Now, in terms of the clustering performance raw numbers, when we just look at the silhouette scores, the image data is clustered better, right? But when we look at the visual inspection, these are better with stacking data. So when we stack the physical properties data with the image data and then cluster, it was not evident in the silhouette score, but through visual analysis, we saw that there was a better clustering performance. There was even less within class segmentation in that case. Okay. So what that meant was we were trying to figure out, okay, since that is the case, there exists other data as well. For example, there exists CT scan data for the same data set. So the idea was in future work, use that CT scan data, stack it along with the physical properties data, the image data, and then do cluster. In the hope that we are able to further remove the within class segmentation. So that's future work. We are still exploring that. And the other thing that we want to do is probably apply the same framework to ice cores, because they come from a similar mechanism. The idea is we would like to apply the same framework to annotate ice cores and try to figure out, okay, what is being found in those ice cores. That's this particular paper. These are some of the references, not all of them. This is all I could fit in this particular slide. These are some of the references. Before we move on to questions, I'll just move on to what I'm doing now. Right. So why I'm going here is we're still trying to get some help with this. So I'll just end with this. So now what we're doing is we're looking at that same region, but instead of looking at the drill cores, now we are looking at seabed imagery. So basically there was a remotely operated vehicle remotely operated vehicle that was taken at or taken down this reef slope. So you have the reef and then the reef just drops down into the deep ocean, right? So those regions, they have these very interesting canyons form. So what this survey did using the ROV submersible rover, so they had a Falco voyage, and this was done by the Smiths Ocean Institute. They surveyed those various canyons in various regions of the Great Barrier Reef. And what they have is, they have loads of elements identified within those dives. For example, there's a shrimp, there is sea star, there is sea urchins, loads of biota or biota and substrate. Substrate is, for example, sand, mud, there is rock, so there's background, foreground, and there's hours and hours of video footage of that particular ROV, which still needs to be flagged. So this is the data that I am working on currently. This is from one of the dives of that particular ROV. They took a 7-hour-long video. From that 7-hour-long video, a student of my supervisor, Jody Webster, went through that 7-hour video and identified each and every organism in that particular video and created this 7,000 labels, 7,000 label data set. Now, what I am trying to do is use that 7,000 image label data set to train a image classification algorithm. Now, where I need help in this case is that annotation was done on a platform called Squirrel Plus, and unfortunately, Squirrel Plus does not export the segment of the image that had just the object of interest. For example, the object of interest is a shrimp, right? But a shrimp is a very tiny organism when we look at the 4K resolution camera image. So there is loads of background and very little foreground. And that's still okay. If we use some kind of automated tracking and object detection to crop, that is fine. But the problem is when we have multiple organisms in one image. For example, if you look at these sections, these are corals, right? So, sorry, these are sponges. So these are all meshed together in one image. So these are crops of just one image. So what we are doing now is we are trying to create this kind of crops for all of the images in this particular die. And there are 5 other dies. So if you have any people that are interested in helping us in this process, we would be more than happy to take on volunteers. So that's it from me. Thank you all for listening. Any questions and comments are more than.
Thank you, Ratnil, for a wonderful presentation. Now we'll take some questions, comments.
Thank you, Ratnil. It was a very interesting and informative presentation. Thank you. Because you mentioned that in that paper that GMM was the method that performed the best.
Yeah.
Did you get a chance to think what could be the reasons, just out of curiosity, what could be the reason that this particular algorithm outperform all others?
What I think is the reason is the ability of the GMM to distinguish the hard and soft boundaries. So the other 2 algorithms that we have, they cluster using hard boundaries. In terms of the data that we have, the coral core, there is the boundaries are very blurred, I would say. So I think that's one of the reasons why the GMM may have performed better.
Okay, thanks. And when you evaluated the algorithms, you used human enabled annotations, right? So you use those information as ground truths. So they're kind of 100% accurate. Would you agree that, or 99% accurate already?
So these labels are 100% accurate. They are annotated by a marine geologist.
Okay, right. Okay, yeah. Thank you.
Yeah. Thank you for your question.
Cheers.
Outside of the algorithms that you mentioned for clustering over here, did you try any other algorithms like density-based algorithms that
No.
have, like in the past, I've seen like they work well with like these very fine boundary problems?
So I did apply dbScan. I did run dbScan, but the problem with dbScan was, since there are many tiny blocks in this particular example, there are tiny specks, it didn't do a really good job at clustering. It was just picking those small rocks and saying that, okay, there are 50 different classes within a particular core. So that's one of the reasons why I stopped using dbScan. The other reason why I did not use dbScan is the same as with the agglomerative clustering. It was taking too long to cluster. So that's why I could not. I started with that, but I could not.
Perhaps this is something you can note in the discussion.
Yeah.
So in terms of,
Yeah, I also wanted to ask, like, there are, I think, a few deep learning based methods for image segmentation. Did you look into that, or how did that?
So in this case, I did do a literature on some of these. So mask RNN is one of the more popular ones, but I did not implement them because the GMM was doing an okay enough job. So I didn't need to implement something more advanced.
But you did observe that even in GMM, I think there were some specs which were misclassified within the segment itself, right?
So for example, this region, and even this brown region, it should just be one. But in the annotation process, since we were doing a manual annotation later on, that didn't really hinder much. So but that is actually very useful if we are trying to improve this further. Thank you for that.
Yeah, I also I didn't clearly understand how you use the features that you were talking about, the code properties
Okay,
Yeah, so how was that used along with these clustered images?
so those features are used to generate these annotations. So assuming that we don't have the actual labels, right? If we just use the result from these various classification models that come from learning those features and this clustered image, we are able to then annotate it. But over here, I am just showing the actual values here as well.
Uh-huh.
So this, if even if we remove this, we are able to find that, okay, there's a supposed to be a massive pearl in this region. There's supposed to be a massive pearl in this region. There's supposed to be some kind of microbialite here. So that's where, so this is generated using the feature set.
I must say that your presentation, your visualization is really good. I think this will be one of our benchmark papers when we tell future students, through the visualization. So what did you use for making all these plots?
Python. So standard Python.
So, but what will happen like in the future if somebody wants to use your software framework? How do they go from?
So what you need is you need the image and you need the physical properties reading for the image. You feed those two to this model and it will give you these two images. And then from there you do a manual annotation.
So can you have like a byproduct of this, like a web page kind of a thing where, like you have like people from the reef community, they may not know how to use GitHub and run it so that it automatically runs in some kind of a system. Like
There
a web
is
page.
none at the moment, but I can do that. So I'll need to go to Travis about this because he did mention there is a tool where you can just put your code there and it will be used to create a website.
Probably Josh as well.
Yeah, I can talk to them about it.
So another thought I had was like,
They can't hear you.
am I not audible? It should be audible. Yes, I was asking was that currently you're working at a pixel level, right? That you are doing the clustering, which you mentioned was like very time consuming, right? It's computationally very heavy. What I see is that even your classified image that you've generated over there, it's working at more of a row level.
Yeah.
Right. So maybe did you try that, or did you think about that? Like if you can generate clusters instead of doing it at a pixel level, you do it at a row level, and you basically in that case, I believe like the problem can be more simplified. Do you think?
It's actually useful info. So initially I was thinking along those lines, but I could not find a way where I could do low level because these are taken at 10 centimeter intervals. So these are pixels at also 10 centimeter intervals, but I could not figure out a way where I could link those two together. So that's again useful feedback and probably something that we can think about offline and try to figure out how can we simplify this further so that we can use the better, or we can use BB scan and even higher resolution for better models to do this.
I think this is a really good work and a good start and a lot of work. There can be a lot of follow-up work after this. So all the best for it.
Thank you. Thank you everybody. Thank you for time.